Hey everyone, you've seen it, I've seen it. The quality of AI-generated images has just exploded in the last couple of years. We've gone from these weird, blurry, almost dreamlike blobs to images that are, well, they're basically indistinguishable from reality. It's been an absolutely wild ride.
So that's the big question, right? How did we get here? How did AI get so ridiculously good at turning a simple string of text into a work of art? It wasn't just one single aha moment.
The real story is actually way cooler. It's about two rival technologies, two completely different ways of thinking that were locked in this epic battle for pixel-perfect images. And that competition? Well, that's what changed everything.
Okay, so let's start at the beginning. Our story kicks off with the first major contender, an idea that was so clever it basically launched the whole modern era of AI art. I'm talking, of course, about GANs.
And this timeline really tells the tale. You see that first big bang back in 2014? That's GANs. For about 6 solid years, they were the undisputed kings of the hill. But then, look what happens around 2020. The pace just goes vertical. This is when diffusion models crash the party and completely change the game, leading directly to tools we all know, like Stable Diffusion, just a couple of years later.
So what in the world is a GAN? Well, the name kind of gives it away, a Generative Adversarial Network. The core idea is to frame the whole process of creating an image as a competitive two-player game.
And here are our two players. First, you have the generator, which you can think of as a master art forger. Its only job is to create a fake image that's so good it's convincing. Then you have the discriminator, which is like an art detective. Its job is to look at an image and tell you if it's a real one or a fake from the forger. They're locked in this endless cycle. The forger gets better, so the detective has to get better, which forces the forger to get even better. It's this constant one-upmanship that makes them both improve.
And for a while, this system was absolutely state-of-the-art. It was genius. But as brilliant as the GAN concept was, researchers kept hitting the same walls. There were some fundamental cracks in the system.
The biggest problem was that GANs are just kind of unstable. That whole balancing act between the forger and the detective, it's super delicate. If one gets too good too fast, the whole learning process just falls apart. This often led to something called mode collapse. That's when the forger stumbles onto one specific image that always fools the detective and it just stops trying. It just keeps making tiny variations of that one successful fake, which obviously kills any hope of creativity or diversity.
And you don't have to take my word for it. This quote from a research paper really hits the nail on the head. These weren't just small issues. They were massive roadblocks that kept GANs from hitting that next level of quality everyone was chasing. The world needed a totally new approach.
And that new approach came from a completely different mindset. Instead of an aggressive adversarial fight, this new idea was all about a slow, careful process of refinement. So let's welcome to the stage diffusion models.
This slide really just lays it all out, doesn't it? On one side, you have GANs, this all-or-nothing competitive game. On the other, diffusion, a patient, step-by-step process. And look at the results. Where GANs were unstable, diffusion is stable. Where GANs lacked diversity, diffusion delivers what we call high fidelity, just stunningly detailed and varied images. I absolutely love this analogy because it makes the whole thing just click. A diffusion model doesn't try to paint a masterpiece from a blank canvas. No, it starts with a canvas full of random noise, pure static, like a block of marble. Then, guided by your text prompt, it carefully chips away at that noise, step by step, until a beautiful, clear image is revealed from within.
So, how does it learn to be such a good sculptor? Well, it's a really clever two-part process. First, during training, the AI learns by doing the opposite of what we want. It takes a perfect, clean image and, step by step, completely destroys it by adding noise until it's just static. This is the forward process. Then, it's trained to do the reverse process, to perfectly undo every single one of those destructive steps. By mastering how to reverse destruction, it learns the art of creation.
Now, this core idea was amazing, but the first versions were, let's just say, painfully slow. It took a couple more huge innovations to turn diffusion models from a cool academic project into the lightning-fast powerhouses we use today.
Two key breakthroughs really stand out. First was something called classifier-free guidance, which is a fancy way of saying they found a much smarter way to make sure the AI actually pays close attention to your text prompt. The second, and this was the true game changer, was latent diffusion. Instead of trying to sculpt a life-size marble statue,
Imagine sculpting a perfect, tiny miniature and then magically blowing it up to full size. The AI works on a much smaller, compressed version of the image, which is way, way faster. This is the secret sauce that makes models like Stable Diffusion possible.
And you can see the results right here in the data. Let's look at the FID score. Just think of it like a golf score for how realistic an image is. Lower is better. Look at Stable Diffusion and Imagen. They just crush the GANs. Then there's the clip score, which measures how well the image actually matches the text. Here, higher is better, and again, diffusion wins by a mile. But now look at that last column, inference time. This is where GANs still have a serious edge.
And this chart just hammers that point home. Diffusion models like Imagen give you absolutely incredible quality, but it comes at the cost of speed. A GAN, on the other hand, can spit out an image almost instantly. This fundamental trade-off between quality and speed is still one of the biggest research areas in AI today.
And that brings us to what's next. Because even with all this incredible progress, this story is far from over. Researchers are now setting their sights on a whole new set of challenges that are even harder to solve.
So what's on the horizon? Well, 3 big things. First, efficiency. The holy grail is making diffusion models just as fast as GANs, which would open them up for real-time uses. Second, understanding complexity. AIs still struggle with things like counting, a bowl with 3 apples, or spatial relationships, a red cube on top of a blue sphere. And finally, and this is a huge one, safety and bias. Making sure these incredibly powerful tools are fair, safe, and controllable is one of the most important challenges for the entire field.
And that leaves us with this final question to chew on. As these models get faster and smarter, as they get closer to creating literally anything we can describe, what's left? What becomes the final frontier when technology can actually keep up with human imagination, pixel for pixel? That's a question for all of us to think about. Thanks so much for watching.